Good afternoon, guys. Hope you're doing well. Welcome to lecture 4 for Chem 111. This is the precipitation lecture. Let's go ahead and get started on this material. I will again share my screen so you can see what I'm talking about. And let's get this party started. Sorry, wrong thing. So we'll talk a little about heterogeneous and homogeneous solution and equilibrium again. Talk about buffer solutions, precipitation reactions, solubility equilibria, separation of ions by fractional precipitation, and pH and solubility. All right. So the first thing I want to talk about is buffers. We talked a little bit about buffers so far. Buffers are solutions of a weak conjugate acid-base pair that resist drastic changes in pH. Though these solutions contain relatively high concentrations, more than 10 to the minus 3, of both acid and base. The concentration of acid and base should be approximately equal. What happens when we have both the HF and F minus? That's a buffer solution. So HF is a weak acid, F minus is its conjugate base. If I have both of those present, if I add an acid or a base to it, then something will happen. Now, if I add an acid to this particular solution, then I'm going to create more HF, less F minus, but there's not much change because the buffer was there. So we've instead of just getting a whole bunch of pH change from all those new H's being in solution, some of those H's have combined with the F minus to make HF. And so we minimize the change in pH. The opposite is true when we add something like a base, like an OH minus. If I add that base, it's going to react with the acid that's in solution, creating more F minus. Therefore, I have not changed the OH as much, therefore not changed the pH as much, or the POH, and therefore it is resistant to change because of the presence of the weak acid and its conjugate base. Buffers can be made in a number of different ways. We can mix a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid, or we can add strong acid and partially neutralize a weak base, or add strong base and partially neutralize a weak acid. Either situation will create a place where I have a weak acid or a weak base and its conjugate. Okay? Let's talk about pH range and the ability to buffer. So the range of pH values over which a buffer system works effectively is limited. We can't do this over, like a huge amount. So our optimal pH is where pH equals pKa. And that happens when we have the exact same amount of weak acid as conjugate base. Okay. Now, if one concentration is more than 10 times the other, buffering action doesn't work very well. And so that means that our pH range for our buffer is usually plus or minus 1 pH unit from the pKa. Okay, that's about all we can get. The amount of acid or base the buffer can neutralize before the pH begins to change to an appreciable degree is the amount that it can buffer. That's its buffer capacity. And using the Henderson-Hasselbalch equation, we can see that the pH will be the same for a conjugate acid-base pair of 1 molar each, as long as they're both the same, as it would be for a solution that has 0.1 mole. Okay, so the pH is going to be the same in both cases, since the acid and base are equal. But the thing is, if you have more acid base in solution, i.e. it's a 1 molar solution, you have a bigger buffer capacity. Okay, so we have more ability to react with the things that are coming into our solutions. Addition of a strong acid or a strong base to a buffer. So adding a strong acid or base is a neutralization reaction. We will calculate the stoichiometry just like we did before to find HA and A minus when all of the added acid or base reacts. And then we'll use the Henderson-Hasselbalch equation to find the pH. So if I have a buffer containing HA and A minus, and I add strong acid to it, I know that the concentration of H plus that's generated from the strong acid is equal to the amount of HA that I added. That will then react with the A minus that's in solution to generate new HA. So what I've effectively done is reduced the amount of A minus present and added to the amount of HA that's present by the amount of moles of strong acid that were added. Then I have a new HA and a new A minus, and then can use the Henderson-Hasselbalch equation to calculate what the new pH is going to be. Or if I have a pH, then I can figure out what the ratio of those things are. All right. In the other part of it, when we add a strong base to this, if I have HA plus the strong base, I'm going to generate more A minus and take away some of that HA. So my A minus will go up, my HA will go down. All right. And that will resist changes in the pH as well. So those are calculations you should be able to do. Now, Henderson-Hasselbalch, let's talk about that again. See in a couple times, this is the derivation from where it comes from. If I have a weak acid and I take the negative log of both sides, I take the negative log of Ka, that's equal to the negative log of the H plus the negative log of the A minus over the HA. I know that the negative log of H plus is the pH. I know that the negative log of Ka is pKa. So I can rearrange this, move this to this side, move that to that side. And I get pH is equal to pKa plus the log of the A minus over the HA. Okay. This equation is known as the Henderson-Hasselbalch equation. I call it the Hasselhoff. It's just an easier way for me to remember it and made it a little less intimidating to me when I was taking this class. So this is how we can calculate those things. As long as we know what the ratio of the A minus to the HA is, or in the case of a base, the conjugate acid and the weak base, we can do that as well. We can do it with the pKb. That's how we can work with it. Okay? How do I use that? I just told you I could. Now let's see how we do. So let's say that we have we want to know what the pH is of a buffer that's 0.12 molar in lactic acid, CH3CHOH, COOH, and 0.1 molar in sodium lactate. The Ka for lactic acid is 1.4 times 10 to the minus 4th. So pH equals pKa plus the log of the base over the acid. So I take the negative log of the Ka plus the log of the base, which is the 0.1 molar sodium lactate, over the acid, which is the lactic acid. I then can calculate what that pH is going to be, and that's 3.77. So we've gone from 3.85 to 3.77. Okay, so that's how I can calculate that using the Henderson-Hasselbalch equation. Provided that I know Ka and the concentration of both the acid and the base, then I can calculate pH. If I have a buffer made by adding 0.3 mole HC2H3O2 and 0.3 mole NaC2H3O2 to enough water to make 1 liter of solution, the Ka of the acid being 1.8 times 10 to the minus 5th, calculate the pH after 0.02 moles of NaOH is added. So I know my initial conditions. I want to calculate the pH, that's the pKa plus the log of the base over the acid. That's equal to the negative log of 1.8 times 10 to the minus 5th plus the log of the 0.3 over the 0.3. This term drops out, and so it's going to be 4.74, the negative log of the Ka. Now, once I add that 0.02 moles of NaOH, so I've added NaOH, it reacts with the acid. So the concentration of the acid goes down. That goes to 0.28. And the concentration of base goes up. The anion becomes 0.32. Those new concentrations are then plugged back into this expression, and I can see that my pH goes up to 4.8. Okay, so that's how we can do that. We have to look at what was my initial condition, how does it change when I add the acid or the base, and how do we get that to work. Okay, and that's all I'm going to talk about in terms of pH and acid base and Henderson-Hasselbalch and buffers. All right. Practice is a good thing for those. I will put up practice sheets for all of that, so you will have stuff that you can practice for. All right. But now we're going to talk about precipitation reactions. We've talked about precipitation reactions in the past. We've used the solubility rules to predict which one of those things is not going to be soluble. We know that this happens eventually. What determines how and when it happens? That's what I wanted. So let's talk a little bit about how precipitation works. So we had two soluble salts, two solutions of soluble salts. So they're both clear, they're both in solution. We mix them together and we form a solid product. That's a precipitate. An example of that would be adding PbNO3 to Ki to give me PbI2 solid plus KNO3 aqueous. Now, we can talk about this in terms of K. Since it's a solubility product, we call it a KSP. But I'm not really interested in the formation of this KNO3. That's not the important part of this to me. What's important to me is that I took the PB here and the I here, and I mixed them together to make this PbI2. That's the only part of this equation I actually care about. So I'm going to write the equation slightly differently than I have done in the past, and we're going to talk about the different ways that we can write those equations. Now, you may have seen this before. Hopefully this is a review. So let's talk about what we would actually look at. This equation that I show here is called a molecular equation because it shows everything as if it were a molecule. We know that this is not the situation that exists in solution. When I put that PbNO3 in solution, I get Pb2 plus 2 NO3 minus. So this is not really the real situation. So then we can talk about an ionic equation where we explicitly show the ions. So Ag plus NO3 minus K plus Cl minus goes to AgCl plus K plus and NO3 minus. Now this is a different equation, but I have shown explicitly the ions that are present there, and I've shown all of the ions that are present there. But here's the thing. Again, we weren't that interested in this stuff because that didn't actually do anything. The NO3 is here, and its aqueous here, and its NO3 is here, and its aqueous here, so it did nothing. It helped me not at all. The same is true with the K+. It's here, it's here, it's exactly the same on both sides, so it doesn't matter. We call those spectator ions because they're not part of the chemistry that we're looking at. So if I want to get rid of the spectators and focus on the guys who are actually in this fight, then I have the Ag plus aqueous plus Cl minus aqueous going to AgCl. So, okay. So these are the three equations that you have, the molecular, ionic, and then net ionic. The net ionic equation is the one that we're talking about when we talk about solubility products. And we want to do it in the reverse of this direction because we want to look at how soluble are those ions compared to the solid that we're talking. All right. Because ionic compounds are strong electrolytes, they dissociate to the extent that they dissolve. When an equilibrium equation is written, the solid is the reactant, and the ions are in the solution of the product. So the equilibrium constant expression called the KSP, the solubility product constant, KSP, is equal to the products, Ag plus times Cl minus. It's not divided by AgCl because that's a solid. So this is the expression for KSP. Now, is it important to write this as an actual ionic equation? Yes. Why? Because if this happened to be like an MgCl2, then I'd have 1 Mg, 2 Cl's, and so it would be the concentration of Mg times the concentration of Cl squared. So I, again, need that stoichiometry to make sure that I'm getting the correct expressions to be able to work with the math in these equations. What we need to know what could potentially be our insoluble products. Okay, so we look at the solubility rules. You've probably seen these before. You'll get a version of this on the test. Salts of group 1A, so sodium, lithium, potassium, rubidium, cesium, francium, all those guys in that 1A column, those in NH4 salts are soluble. Okay, NO3 minus salts, ClO3 minus salts, and ClO4 minus salts are soluble. Cl minus, Br minus, I minus are soluble except Ag plus, Hg2 plus, Pb2 plus, and Hg2 plus. Those are going to be insoluble exceptions to Rule 3. For 4, the sulfates are soluble except for Ag2 plus, Ba2 plus, and Pb2 plus. Okay, so those are exceptions to the solubility in Rule 4. In 5, OH minus are insoluble except for rule 1, i.e. the group 1s and the NH4 plus, and Ba2 plus. OH2 is soluble. So those are the exceptions to rule 5. CO3 2 minus, PO4 3 minus, and S2 minus are insoluble, unless they've already been deemed soluble based on the rules above it. So the rules have to be applied in order. We take each compound and look at, is this soluble based on these things? And if you find it soluble in this one, it doesn't matter that it's listed as insoluble later because you've already applied the first one. Okay? So those are the rules that we have. So I want to talk about, let's do some predictions. PbI2. PbI2. Is it going to be soluble or is it not? Well, from the rules that we looked at, it says that I minus are soluble except for Pb2 plus. So it's insoluble based on rule 3. When we talk about AgNO3, let's go look up here. Ag is not a group 1 thing. NO3, however, is soluble. So it's soluble via rule 2. NIS. Well, Ni is one of those things that I don't really know. S2 minus is listed as insoluble, so it's insoluble based on rule 6. CuClO42 ClO42 CuClO42 ClO4 minus are soluble. So rule 2 says that that particular one is soluble. Rb2CO3, looking through my list, I don't see Rb as any of the things that are going down, so I'm looking for CO3 2 minus. Rule 6 says that those are insoluble, so it's insoluble based on rule 6. Too far. NH42SO4. NH4 plus are soluble based on rule 1. Okay, so it is soluble based on that. All right. And PbSO4. PbSO4. So SO4 2 minus is soluble except for Pb2 plus. So via rule 4, that one is insoluble. Okay, so that's how we know the solubility of those guys. All right. And that's how we apply those. Now, like I said, there will be a version of that on the test. You will need to determine which one of these may be able to become solid, to be a solid product. And so we need to look at its solubility. Okay. So, for example, BaSO4 solid goes to Ba2 plus SO4 2 minus. Equilibrium constant KSP equals Ba2 plus times SO4 2 minus. If we talk about Ba3PO4 2, it goes to 3 Ba2 plus 2 PO4 3 minus. The KSP is equal to Ba2 plus to the third times PO4 3 minus squared. And we need to consider the reaction quotient Q that's related to K. If we have a situation Q, we're not in equilibrium, and we can determine what is going on with that. Now, if Q is less than K, I don't care. Q is less than K, I haven't hit equilibrium yet. So I will never form a precipitate in that case. If Q is equal to K, then that's defined as a saturated solution. And I have not formed a solid. The only time when I form that solid is when Q is greater than K. So that's a supersaturated solution, and so precipitation will occur then. So if I have not gotten to K, if Q is too small, then I form no solid. So the concentration of the ions will be determined, not be determined whether the solid product forms or not. Okay. Now KSP, the solubility product constant, is not the same as solubility. When we talk about solubility, we're not talking about solubility product. KSP is a solubility product. It can determine the molar concentration of those ions based on the KSP. Using the empirical formula, I can then determine the molar solubility of a compound. And from there, using the formula weight, I can determine the mass solubility in grams per liter. So when we talk about solubility for these particular things, we talk in moles per liter or in grams per liter. Okay, that is typically the way that this happens. All right, solubility is a quantity of a substance that dissolves to form a saturated solution. All right. So the KSP for CaF2 is 3.9 times 10 to the minus 11 to 25 degrees. What is its molar solubility? So we follow the same format as before. CaF2 goes to Ca2 plus 2F minus. KSP is then Ca2 plus times F minus squared. And that's equal to 3.9 times 10 to the minus 11. Since I know that Ca2 plus is going to be plus x, and F minus is going to be plus 2x, and it has to be squared, I then end up with 3.9 times 10 to the minus 11th equals 4x cubed. I solve for x, and I get 3.25 times 10 to the minus 12. That's the molar solubility for that particular compound. So your Ca is based on that. Your F minus at equilibrium is going to be twice that. Okay. If I want an answer in grams per liter, I'm going to multiply by the molar mass to get that in grams per liter. Okay, so that's my molar solubility for that particular compound. Fractional precipitation. Okay, awesome. What the hell does that mean? Well, every single thing that we talk about has a KSP, right? So I'm going to form a solid, but only when I get to a concentration that's higher than the KSP value. And all of those are different. Now, how different they are is relevant because I can look at a combination of things in solution and add materials to it to selectively precipitate some of the materials that are in it. If I choose carefully, I can precipitate one ion, remove all of it, and then precipitate another ion and remove all of it. So careful setup allows separation of the ions. The ion with the smallest K precipitates first, and we need to be able to describe that process and use it to predict what order the ions will precipitate, or use it to choose a solution to use in such a precipitation, and why you would use it. So what am I talking about? I want you to be able to tell me that if I have 3 ions and I have 3 K values, that based on those K values with this particular other thing, right? This one's going to precipitate first. This one will precipitate second. This one will precipitate third. You want to describe that process. You also need to be able to predict, based on the ions that you have, what is the best thing to add to this to get a selective precipitation. Okay, so that's the kind of question that you'll see about this. This just means that I can effectively decide what precipitates when to get those out of solution. And this is one of the ways that we do separation of ions in the laboratory. Okay? Factors affecting solubility. So let's look at our salts. So a salt whose anion is the conjugate base of a weak acid, the solubility increases as pH decreases. The anion is the conjugate base of a weak acid. So F minus, anion, conjugate base of HF. The solubility will increase as the pH decreases. So the solubility of F will go up if we take this H plus out. Okay, so this will become more soluble as this goes away. All right. That also means that Pb2 plus that's in solution will increase in its ability to be there. Okay. Salt of an anion is conjugate base of a strong acid. Salt is unaffected by changes in pH. Okay, so we need to look and say, all right, if I add H plus, I'm going to derive F minus 2HF. So the F minus is going to decrease. The Pb2 plus that's there that came from the PbF2 is then going to be a higher concentration since the F minus is lower. So buffers control pH. When a buffer is used, there's no change in concentration of the hydroxide ion. So this is not something that we can deal with in a buffered solution. Okay? Amphoteric oxides and hydroxides. Amphoteric are soluble in strong acids or base because they can act either as acids or bases. That's what amphoteric means. So examples are oxides and hydroxides of aluminum, chromium, zinc, and tin. Let's talk about aluminum hydroxide. So aluminum Al3+, if it's in water, I get AlOH3. That's an insoluble salt, and so it comes out of solution. So if I add additional H+, I can derive the AlOH3 out of solution and make it Al3+. Okay? So if I have AL3, ALOH3, and I don't want it there, I can add an acid to it to get rid of that material. If, however, I want that ALOH3 to go into solution, to change the solubility of the Al, one of the other ways that I can do that is to add additional OH minus. Because if I add additional OH minus, I form a complex, and that means that that is more soluble than it was. So these are ways that I can use pH to effectively change the amount of some of these ions that are in solution. So Al3 plus, Cr3 plus, Zn2 plus, and Sn2 plus, all of these will work in similar ways. So adding acid will make them more soluble because I get less of the hydroxide, and adding hydroxides to them will make them more soluble because I form a complex. All right. One other thing that we need to talk about is Henry's law. When we talk about precipitation, we normally talk about solubility of the aqueous ions, but we also need to talk about solubility for gases. So the solubility of a gas is proportional to the partial pressure of the gas above the solution. So if I have more of that gas above the solution, I should get more in the solution, all right? So if I'm in equilibrium and I increase the pressure on this particular guy by moving that piston down, pressure's higher, more CO2 dissolves. That's why my soda bottles are overpressurized, because it keeps the CO2 in solution, all right? Now, this solubility is based on K, which is Henry's law constant, and the pressure of the gas above it. What I need you to understand is that the solubility of the gas is proportional to the pressure of the gas above that solution. Now, you may be asked to find what a K is based on the solubility and the pressure of the gas. If you're given solubility and pressure, I would hope that you could solve for K. One of the things that you'll see over here is that O2 has a higher solubility at the same pressures than CO does, than N2 does, and then HE does. And that means that the K for O2 is bigger than the K for CO, is bigger than the K for N2, is bigger than the K for HE. So that's something that you should be able to interpret from this graph. So if you see a graph like this, you should be able to compare those K values. Not tell me what they are, but tell me which one's the biggest and which is the smallest. And you should be able to find a K if given the SG and the PG. Okay? Dun dun dun. Well, that's everything that I had for that particular chapter. That's all I wanted to talk about in terms of solubility and the ability to talk about those. Now, how might you see that on a test? You might see, hey, I have this particular solid, I have dissolved it at this concentration, tell me what's going to happen in solution. So you need to calculate for me what is the Q, compare that to the K, and tell me, will it precipitate, will it not precipitate? Okay, that's something that you need to be able to do. Based on the value that you've calculated, you should be able to tell me if I can get more solid to dissolve, or if that solid is going to fall out of solution. So are we favoring the forward reaction, dissolution, or are we favoring the reverse reaction, making that solid and forming a precipitate? You should be able to tell me how changes in pH can affect those ions that it is effective on. So those four that we talked about are things that you should be able to talk about. What happens if I change the pH with those solutions? Okay, so that's something that you'll need to be able to deal with. Other things, you will get asked, what is the solubility of this material? So how much can go into solution? That's the Rice table that I showed you, calculating solubility from KSP. You may get asked to calculate a KSP. Things of that nature. Those are the kinds of things that you should see. What will you see exactly? I'll give you a practice for what I would expect you to be able to do based on what we talked about today. You should be able to do some of those things. So that's what my expectation is. I will get those practices up as soon as I can, and I hope you guys have a good time with that lecture, and I'll talk to you soon. All right, bye guys.